So I'm Doug Ort. I'm with a company called Hosokawa Polymer Systems, used to be called Polymer Systems, Polymer Machinery. We're a recycling company. I've been here 21 years, and I worked for another Hosokawa division specializing in just process equipment, mixing, fine size reduction, things like that, for like 7 years before that. So Polymer Systems is located in Berlin, Connecticut. It's over 50-year history. We supply primarily granulators, but we started to branch out in the last decade to a lot of other things too. So we have shredders, we do washing lines for post-consumer, post-industrial material. And really one of the other big things that we've sold a lot of is dedusting systems. I'll mention that at the end of this. So we've done a lot of systems work, like I said, just a few pictures of some of the things that we've been able to do. So if anyone has real complicated projects, I'm assuming most of you guys are injection molding, just knowing Andrew and George's territory and who their customers are. But we also get into really big recycling lines, wire and cable recycling, all different types of stuff as well. So what do we hear about? So we're here to keep dust out of your regrind. Everybody wants clean regrind. There's a ton of benefits to have clean regrind, a lot less headaches. I'm going to do my best to give you all the hints that we and tricks that we use when we're working with customers. And if you have any specific problems, I'd be more than happy to try to answer them today, or we could try to answer them at a later date. And it doesn't matter if it's our machine or somebody else's. We'd be more than happy to help you guys. So what are the negatives to dust? Why are we all here? Well, for sure, it makes bad parts. Depending upon what the material is and how much dust you have, is going to tell you how many bad parts you're going to make, but dust does not help processing at all. It's also a huge maintenance headache. Can cause a lot of issues for maintenance on the machines and on the auxiliary equipment. Processing time, downtime because of dust is high. Loss of material. Believe it or not, this is not a picture of a motor in some box outside in a snowstorm. That is dust in the back of a granulator inside a factory. So, you know, it may only be 0.5% or 1%, or it may be up to 8 or 9%. That's a lot of material loss. Cleanliness is important, and it's a hazard itself. So we want to minimize dust. Positives, I can't think of any. I'll tell you a quick story. I was at a trade show, and we had our deduster, and we had some people from a company come up and ask what it was and show some interest. But then when I told them exactly what it did, they're like, well, you know, we use PVC. We try to make dust so that we can process with PVC powder. And I go, well, PVC powder is a lot different than dust. PVC powder is flowable. It's 0.5 to 1 millimeter. And you really don't want the dust. And they're like, well, you know, thanks a lot, and went on their way. A couple years later, in fact, last year, they came back to us and bought a big pipe shredding system with us, and they were adamant that they wanted dedusting to go with it. So there's a big difference between dust and powder, and there's a huge difference between dust and regrind, as you guys know. So why don't you want dust in your material, in your regrind, in your processing material? Because it causes bad parts. It costs money. So you can see here some PET preforms, and for sure you can see the burning on one of them. A lot of that's caused by dust, can easily be caused by dust. I'll give you an example of that a little bit in the future here. Actually right now, sorry. So we had a customer with polycarbonate parts. I think they were Petri dishes, and they were making an awful lot of reject. Some of the information is with the runner and the part reject, it was 22% by weight. The material cost for what they were doing was $2.45. So actually what they came to us for was to get the dust out, which we did. So they bought a deduster from us and greatly increased their efficiency. However, they were losing about 5 or 6% of their material. So we worked with them on what I'm going to go over with you here, And by the end of it, they had increased their yield, if you want to call it that, by 2%. So they had 2% less dust that they were pulling out with the deduster. And overall, the way that these guys run, that dust saved them $6,000 a year, in addition to not having to dust in the material because of the deduster, and especially with these thin polycarbonate parts, and their reject rate also saved them additional money. So, you don't want to make bad parts. That costs money. But what else costs money is downtime. If you have loaders, if you have central systems for moving material around, they all have filters, and dust clogs those filters very quickly. It's a maintenance nightmare. You don't know how often you have to do it. Obviously, or sometimes you run into problems before you've been able to change them, and then you have lines down. General housekeeping. You just want your shop to look nice. You want your floor to look nice and the plant to look nice. You don't want dust all over. It's dangerous as well to have that dust around. And it can cause all kinds of problems on whether it's extrusion in the feed throat of an extruder. The dust will start to build up and then plug the extruder, or injection nozzles, things like that. There's a lot of processing issues. I'm sure you have a lot more that you guys run into in the field. But in addition to losing money because of the dust, it's unhealthy. It costs time. It's employee morale to have a plant dusty. This is by far one of the extreme conditions, but the granulator on the right there, it's just covered in dust. And when we opened it up and looked at it, it was pretty obvious why. The knives were all chipped, dull, and their evacuation was horrible. But it's just something you don't want in the plant, especially to this extreme. It's a health hazard for people breathing in if it gets to too high a point, especially if you have glass-filled material, things like that. People can slip if it's on the floor. And then the worst case scenario, it very rarely happens, but it does happen, and it's something that everyone needs to be aware of. Not all, but most of this fine dust is combustive and can catch fire. So if you're looking at the right there and you see that granulator with the word dust in it, the granulator itself is all steel. It's not going to catch fire, but with all that dust on the outside of it, that certainly can catch fire. And usually what causes explosions, and the one at the bottom there is a pipe manufacturer. It's not the one we sold our equipment to, and I don't think they have our equipment, but in any event, it's a pipe manufacturer. And they had so much dust in the plant that they had some type of ignition somewhere which rattled the rafters, and all the dust came down, and that's usually what happens. And then you've got a high concentration of dust, and then they had an explosion. So it's just something you have to be wary of and certainly take care of. We're trying to minimize it so that you don't have to do as much maintenance and cleanup. So with that, what causes dust in regrind? So these are the key elements to what causes dust. Some of these are like a one-time set it and forget it, and others are things that you're going to have to keep an eye on over time. So for all you that have granulators, you've got an RPM, whether it's a slow speed or a high speed, doesn't matter what it is, it's running at some certain speed, and then you're cutting material between a stationary and rotating knife. You've got a gap between that stationary and rotating knife. That influences how much dust is in your regrind. The sharpness of the knives does as well. For those of you that have granulators with screens, the screen has a big influence on the dust. The overall geometry of the machine, number of knives, chamber design, so forth, and that's pretty much set. So whatever you have, you're going to live with, but that's something when you're buying new equipment you can take a look at. Your material certainly has a big influence on the amount of dust that you can generate. How you transport it out of the granulator to process them, to use it downstream. And then if you're using anything with any type of filter, the potential for back pressure. So I'll go over all these in more detail, and we'll go through them one by one. So the rotor speed, I mean, it's somewhat obvious, a higher speed, you're going to get more cuts per revolution. It tends to get more fines because you're getting more cutting action. It also gives you a higher capacity. So Again, I'm assuming a majority of you have like press side units where speed and capacity is usually not as much of an issue. We have a lot of customers that are doing, 2,000, 5,000, one customer doing 12,000 pounds per hour. Capacity is real important to them. And then lower speed, obviously, the slower you go, the less cuts you're going to have, your capacity drops off, but you're also going to generate less fines. And then, the question is, well, where should we be? It's not an exact science, but I can tell you this, I always take things to the extreme. If you have a granulator, it's running at 5 RPM, you're not going to cut anything because everything's going to fall down. The knives won't have a chance to get the material between them to cut it. So obviously that's too low. And if you're going at, let's say 5,000 RPM, the material never has a chance to get down below the rotating knives because it just keeps bouncing on top of it. So we know we're somewhere in between. And just from our years and years of experience and testing, what we found is most standard press side granulators, even large capacity granulators, they're running nominal speeds between 450 to 550 RPM, maybe 400 RPM. If you're doing films and fibers, it may be as much as 1,000 RPM because you want to get a lot of cutting action. And then we have what's called a slow speed type. And when you're using a screen, we usually don't like to go too much under 200 RPM. And for ours, we go 2 to 350 RPM. Most of you probably have 1,800 RPM motor. That's what most granulator companies use to get their speed for the rotor. If you wanted to go to a slower speed, one of the things you can do, you can either change the pulleys. You can make the one on the motor smaller, or you can make the one on the rotor larger. Sometimes that's hard. It's already in a guard. Most of the manufacturers try to make the largest one they can because it gives you more inertial force. So you really can't fit a bigger one on the rotor. And if you go too small on the motor, you're going to get belt slippage. So you can try a different size motor, RPM motor. Now, the only thing I'll say with that is when you go from 1,800 to 1,200 RPM, the motor frame size changes. So if you have a 10 horsepower, the frame size, I believe, would be 15 horsepower. Even some is a 2 frame size change, so it might be like a 20 horsepower frame size. So you just have to make sure it fits. And then always remember, as you slow things down, as you run slower, you're losing your torque and your momentum. So things that you can do to make up for that is to use a solid flywheel at lower speed. You still have all the momentum you need because of the extra mass to cut through thick walled parts or heavy duty parts. Knife gap, then, I would say this is probably, this and the next one would be the two critical ones. Everybody knows it, but it's just, if you don't have a routine maintenance, it doesn't get checked all the time. It's not so easy to keep it in place like it should be. If you have a tighter knife gap, you usually get a better, nice, clean cut. It generates less fines. You're cutting through the material. You've got the stationary knife, the rotating knife. The material goes right in between, gets sliced like scissors are cutting it almost, and drops out. When the gap starts getting bigger, you start tearing material more. So not only do you generate more dust, but the regrind's not as nice. It doesn't flow as well, causes problems. So what should your knife gap be? So for conventional granulators, a good rule of thumb, 80-20 rule, maybe even 90-10 rule, is between 4 thousandths and 12 thousandths of an inch. If you get into film and fibers or real thin material, even some real soft materials, you want to go finer. Film can slip through, real fine film can slip through if you only have like a 12 thousandths gap. And soft materials tend to tear more. For instance, like fishing lures, rubber worms, things like that. When you're cutting them, you could pull those apart. When you pull them apart, it's not a clean break most of the time. And that's what you'll get if you have a large gap. You'll get those little tails that you see. If you have a rigid material, friable material with a lot of fillers, whether it's glass or TiO2, calcium carbonate, you can live with a little bit bigger gap. That material will tend to break. If you have a runner and you can actually break it in your hand, you need to cut it, but you also don't need such a tight knife gap. One exception to this that I'll say is if the material is running real hot, or on a lot of our real large granulators where we have 200, 300, 400 horsepower, you have to be careful. If you set the knife gap at 4/1000ths of an inch, you have either real hot material like you're running gas tanks or collapsed Parisons, things like that, or you're running huge volumes, thousands of pounds an hour. There is an expansion of the granulator, and the rotor tends to expand faster than the chamber. So if you have a tight knife gap, you could run the risk of knife-to-knife contact, and it happens slowly, so it wouldn't necessarily be catastrophic where it would just stop and break a lot of things. It'll start to grow out, and then you'll chip all the knives. I've seen it happen, and they just ruin a knife set. Luckily, they catch it before it gets worse than that. One thing you can do that's kind of neat is to sort of get an idea of what influence the knife gap really has is get a piece of cardboard, get a box, rip off a piece of cardboard, get a pair of scissors, and cut the cardboard. It cuts relatively easily. Then put a feeler gauge, and I'll show this in the next slide, but put a feeler gauge between the two blades down by the base and try to cut the box. And it still cuts pretty easily. Maybe a little bit harder, but it still cuts very nice and clean. And then if you put a bigger gap in there, a bigger feeler gauge, like 30/1000ths, 40/1000ths, and try to cut the box, it's really hard to do. It doesn't just cut right through. It rips the box, and it tears it. So if you look here, here are scissors. Here's what I mean by putting a feeler gauge in between, like you would use for gapping the knives as well. Here we are with a zero gap just with the scissors. In this case, we had 7/1000ths and 40/1000ths handy. So we used 7/1000ths, and it's still a clean cut. We didn't go as long, and it just gets a little bit harder as you're out away from where the force is in the pivot point. So it was harder to cut as all the way up. And then in the 40/1000ths, you could see the tearing. So it definitely makes a difference. And this is with cardboard, right, which is pretty easy to cut. You can imagine what it's like for plastic. So plastics even makes it that much harder. The knife gap also has an effect not only on dust, but also on the regrind quality, and then also on the power consumption. It's not a huge difference, but with a bigger knife gap, with dull knives we'll get to in a minute, you're consuming a little bit more power to eat through that material. Sharpness of knives is extremely important as well. Again, this is relatively self-explanatory, but you want sharp knives, and what does that do? It generates less dust because you're cutting right through the material, and the regrind quality is better. So every time you make less dust, you're also improving the regrind quality, which just makes things flow better through your system. If the knives are dull, you definitely generate more dust. The regrind starts to tear. You can flatten the regrind out. You'll see white edges on the regrind, and that regrind flow is pretty poor. As a rule of thumb, about a 32nd of an inch radius is the starting of a dull knife. The knife should be almost razor sharp when you start fresh with either resharpened knives or new knives, and as they start to wear, you're not as worried about cutting your finger on them just by touching them. Not saying that you should be rubbing your finger on there, but I'm just saying, a 32nd of a radius starts to get a dull knife. If you have real soft material or films or things like that, you may have to change them at that point, depending upon your capacity that you need. If not, you can let it go a little bit longer. When you have rigids, you can let that go longer. You can let it go twice as long almost. Because the rigids are going to break, you are going to still generate a little bit of dust, but you don't want to be changing the knives every day either. As a tip, one thing, especially high capacity users do, but it's good for everybody, is after you install a new set of knives and set your gap and you're running, go back and re-gap it. Now, when you do that is really up to you. It's up to the material that you run and the capacity, but it really makes a huge difference. Because what happens is that fine tip wears pretty quickly, and depending upon the geometry of your granulator, right here we have a really high shear, steep angle cut. So this is coming out perpendicular to the chamber, and this is coming down. I think this angle is close to 70 degrees. So that's good, because as the tip starts to wear, the gap doesn't increase because it's not radial in line with this, it's at 70-degree angle. That being said, there, especially higher capacity granulators, usually don't have that steep of an angle. So as they wear, you start to increase that gap. So by adjusting the knives, especially if you have bed knife adjustment where it's real easy to adjust, you definitely get a lot longer life and runtime out of the knives, and it'll last longer and you generate less fines. Damaged knives. So hopefully you don't have too much of this. Hopefully you don't have any of it, but it definitely happens. Something gets in there and chips the knives. Obviously, when knives are chipped, they're not going to cut well. They generate more dust. That being said, if you have a knife that has a small chip or two, you don't have to resharpen the knife to completely get rid of that chip. You can, but that may cut the life of the knife down by 20, 30%. You can just, as long as you have, say, 80 at a minimum and really 90, 95% of a good sharp knife, you can leave a small chip or two in there. Our big recyclers do that all the time just because they're always chipping knives with all the different tramp they get in there. So look at your regrind. It'll tell you a lot. Here, the green one, you could see that if you look at this white streak here, that was a dull knife and there's a big knife gap, so it didn't cut through. You could tell that the material's softening, and you could see the smears that are happening on the material. So in general, whether it's the airflow's not right, whether it's the knife gap, or whether it's the sharpness of the knife, or all three, this is really bad looking regrind. Here's a bottle cap, relatively thin material to start with, but you can see like an X here. And again, that's too big of a gap for this material. This one is kind of hard to tell. You can tell it doesn't look good, but it should be really three-dimensional, and it's flattened out. So this had a really big knife gap, dull knives. You could see the white on the outside. You could see the tearing, and this just generated a ton of dust. So they were not managing their knives real well. So here's some good regrind. Here's what nice regrind looks like, new knives, tight knife gap. The first picture here is of some tubing. I think it's maybe like 3/16 tubing, maybe a little smaller. You can see how nice and clean it's cut. This is thin material. I think it's an ABS, so you can see that maybe it broke a little bit, but nonetheless, it's clean. You don't see any hits on it. You don't see any tears, things like that. This is multi-layer high-density polyethylene. It's from gas tank manufacturer. So it's nice three-dimensional, nice clean cuts. You don't see it pounded out. You don't see it flattened. You don't see white marks or knife marks across it. So you can tell a lot by looking at your regrind. Screen also has something to do with dust. So smaller holes obviously make a finer product. When you're making a finer product, you're cutting it more, it's staying in the chamber more, you're going to generate a little bit more dust. You obviously get a little bit lower capacity as well, depending on the hole size, as where when you go with a larger screen, the regrind will be a little bit bigger. Obviously the dust will be less and the capacity will be higher. As the screen starts to wear, and it takes a significant amount of wear before you really see any effect on dust, but as it wears, you tend to hold the material inside the chamber longer because there starts to get a bigger gap between the screen and the knife, so it can sort of sit there, so you can generate more dust. So let me just skip to the bottom and say this real quick. A tip that we use, just because you're using a certain screen size doesn't mean it's the right one. If for some reason you're using a 3/16 and you could be using a 1/4 inch, but it came with a 3/16 screen, it's something to look at. The bigger the screen, it doesn't just generate less dust. It also helps with the uniformity of the material, lower horsepower, lower heat, higher capacity, all those things. So you really want to maximize the screen size in your granulator to use the largest screen you can so that you're processing properly. I know that some people have small injection molding machines. They have to use a small screen. So if you do, you do. That's no problem. I'm just saying that if you can use a larger screen and it doesn't affect anything, then you should do it. One thing I'll mention is some people don't use would use a 1/4-inch screen if they could get away with it, but because of their runners, let's say, they get longs through the screen. Most granulator companies do offer an angled screen, which is a drilled or milled hole at usually 30 degrees opposite to rotation, and it does prevent longs as long as it's inserted the right way. If you have it backwards, it's a long generator. You'll have longs flying through the screen to no end. But that way you can get a little bit larger regrind and a little bit bigger hole without getting the longs that you would get through. The other things to look at, and this is more when you're buying a granulator, is the circumference. You know, how much screen area does the screen have? You know, some have as little as 110 degrees, where 180 would be perfectly, half of a circle. Some of as high as 170. So the more open area you have, the more likely the material is to drop out when it's the right size. That'll generate less fines and less heat, higher capacity, all that. And then the closeness of the holes. For most press side operations, 45 to 55% is a standard, and that's a good standard. If you have really heavy duty large machine, sometimes we'll use a little bit less to give a thicker screen and to give a little more room between the holes to give a stiffer screen. Basically, smaller holes generate more fines and larger holes will generate less fines. On the geometry, so you're stuck with what you have, but I'll just mention this for future purchases. You know, there are two main types of geometry in a granulator. There's just a top feed, which is where the material drops down right on top of the rotor and the screen is right underneath that rotor. And then there's a tangential feed where the material drops down on the downstroke of the rotor, sort of behind the rotor. And that's really good for big voluminous parts. But what happens with that, and it doesn't make a huge deal, but all these things start to add up, is the tangential feed material tends to sit a little bit more over in that belly of the tangent and get cut a little bit more before it gets to the screen. So they do tend to generate a little bit more fines than straight top through type 1. And then the other thing is the rotor geometry. So obviously granulators come with different amount of knives, different amount of bed knives and rotor knives. From the simplest, I think, is a 2-blade rotor and 1 bed knife, which can be fine if you don't need a high capacity, to something that may have as many as 10 rotor knives and 6 bed knives for film and fiber. And just the more cutting you're going to do, the more fines you're going to have. And then we come to material. So there's not too much you can do on material because you have what you have, but just to be aware of what you might want to do in your granulator with the different materials you have, I'll go through them. So when you have soft material, again, like the fishing lures or maybe some flexible PVC or TPO, different rubbers, even some HDPE, you usually want a relatively tight knife gap because the material cuts very easily. If you have a wider knife gap, the material tends to generate these like tails off it, little real light, thin areas that can fall off in transport. And it's not a nice uniform cut. So soft material, tight knife gap, and then you should get low dust. I mean, the material, once you're cutting through the material, there's no reason for anything to come off that material. So the amount of dust that comes out of soft material is usually very low. There is one exception, is if your material is real hot when it comes out. And a trick that we like to tell customers is if you have a runner and you have a 2-minute cycle time, you don't want to necessarily, and a big thick runner that can be hot inside, you don't necessarily want to take that out and drop it right into a granulator. If you can change if you're using a robot, if you can change the robot so that it comes out and it holds to help cool it down a little bit, you could even put a fan in that area, and then drop it, and the robot goes back to its sequence, rather than the robot just waiting to for the platens to open up and pull the next one. It could be cooling the part down. It definitely makes a difference, because we do see dust generated from material smearing inside the granulator sometimes, and sometimes if it's bad enough, they'll generate streamers, which people are doing HDPE know about, and if you have high conveying velocities in your ductwork, you know about. And then nylons, or hard material, nylons, ABS, polycarbonate, PEEK material, is just going to generate more dust, because, you know, even though you're cutting through it, it's going to tend to snap or break as well through the granulation process. And filled material even generates more, because you're always liberating a little bit of that fine powder or the fine fiberglass, or whatever is in there, if it's carbon fiber, that's in there as well. So just so you're aware of how the materials process. And then, okay, so you've ground the material, you've generated the least amount of dust you can, you've got it in the discharge bin of a granulator. How do you get it out? A lot of people, probably more than half, use a blower, blow it over to a cyclone, and then to some type of surge bin or some type of holding bin. Well, if you look down here, you know, this is a blower. This is a material handling blower. It's one just like we use. Material's going to come in, the blower's generating the airflow. It's going to come in, it's going to get hit a little by these paddles. It's going to go to the periphery and then blow down to the cyclone. Well, this is another divisions, but this is a Hosokawa pulverizer, and this is specifically designed to pulverize material, not necessarily plastic, but calcium carbonate, sugar, things like that. The material comes down and in through the center. This is rotating, to be honest, not much faster than a blower would rotate. This may be running at, and here we do use tip speed versus just RPM, but anyways, it's running about the same, maybe 20% faster, and we're pulverizing by impact. The one main difference is, obviously here we have more blades than we do in here, and there's a real tight knife gap between this liner that's in here and here, so the material bounces around, and then we're trying to pulverize it, and it gets pulverized better. Where once it goes into the blower, it does hit the blower wheel, but as soon as it's past the blower wheel, you know, there's no other impact. But just to bring that to your attention. So what can you do about that? If you have filled material and fiberglass material, if you have polycarbonate type material, you know, you probably don't want to use a blower, or if you do use a blower, like in this case, oh, whoops, sorry. In this case over here, you want the blower to either be downstream of the cyclone or on top of the cyclone, so the material comes into the cyclone and discharges and never hits the blower. In this case, the material's discharging, going through an airlock and a deduster, but it's not hitting the blower, so we're not generating any more dust. Obviously, the other thing for press side units is to use some type of loader or central loading system, so it's not going through a blower. You're not going to generate any dust through a blower if you're not using a blower, or if the blower is downstream of the cyclone. So if you're using a loader central system with filters, or if you're using cyclones with filter, you need to pay attention to the filters as well. So we'll look at the bad examples first. So what's a cyclone supposed to do? It's supposed to separate the air and the material, and it separates, a good cyclone separates all the air from all the material. So the air would go out top, material drops down the bottom. In this case, you could actually see that, you know, we've got a positive pressure on top of this Gaylord cover, and here the same thing. And why is that? It's because they're using too small a filter area for the airflow that they have, so the air's trying to go anywhere it can. If the cyclone's sized right, if you have a correctly sized cyclone, there should be no air discharge out the bottom. It may look like it because material's coming at it, it's moving air as it moves, but if you took a piece of paper and put it at the bottom of the cyclone, it would actually suck it up to the cyclone. So, you know, these people just need larger filter area. They don't need this much, but just to give an example, on larger systems, you know, you use a plenum with multiple filters, and so that because everyone who uses filters know they fill up with material over time. We use a reverse plenum on the big projects, so that they're never cleaning the filters. They can come over and just tap the filters and they don't have to unzip them and empty all the material that's out. So I just wanted to emphasize, there's some things that you can't change. The granulator you have, I mean, there's no sense in buying a new one if it works. The geometry of the granulator, things like that. So all that's kind of set. You can look at the RPM. If you want to make a change, you can change the RPM either through the shivs or through the motor, like I mentioned. But the main things to check, and these are ongoing maintenance things, are knife gap and sharpness. If there are two things to take away from this, and I know that you all know this, but set up documentation right at the granulator. Set up something that's put, on the hopper of the granulator, big letters, when were the knife changed, what was the knife gap, who did it, so that people take responsibility for it, and it'll make a big difference. And not only set the knife gap, but go back and readjust it. It will make a big difference. Sharpness, check the sharpness, make sure if they're getting dull that they get resharpened. Check the screen condition. Again, the screens usually last a long time, unless you're running, real high capacities or glass filled material. They still should last quite a bit longer than the knife sharpness. And the filters and wear of a blower wheel as well. How do you know when a screen starts to wear? If it's a round hole, which 99% of them are, it'll start to oblong. So if you have a 1/4-inch screen, you'll start to wear a little bit on the opposite side of rotation, and that's okay. But as that starts to wear down, say most screens should be a 1/4-inch thick. Some are a little bit thinner than that, I know. But once you get to like half the thickness of the screen on that oval, you should either flip the screen if it's reversible, which you definitely should do anyways, or you should change the screen out. And why did I put a picture of a bear there? Well, for one thing, it just catches your attention. This is my back deck, and this is a bear that visits us at least once a week. And the other thing, if this bear can do his routine every Monday night, which he does, every Monday he comes by our house and our neighbors' houses because Tuesday is garbage night, then you guys should be able to either do or have your people, routinely check at least the knife gap and the sharpness of the knives. So you've done everything we said. You've got great knife condition. Your screens are new. Everything's cutting well. You're always going to generate a little bit of dust with a granulator, and the process that you're running just can't live with it. So what do you do about that? I won't go into too much detail on this. I'll just mention that, we do sell a lot of dedusters. We have a lot of really good dedusting technology. And this unit here we came up with last year, it's a KSP, it's a mini deduster. And George and Andrew, actually have this. They could drop it off, you could test it. You could send them material, they could test it and videotape it. If you wanted to do any bigger tests, we do them here. We'd be happy to do that. The only thing I would mention on this is because it's a small unit, something you can put in a car and drive around, really need the regrind to be about a 1/4-inch thick or so for it to work. It may be a little better, but we don't want an expensive and big heavy airlock. So we just have a slide gate here, a manual slide gate. So the flowability of the material works best at a 1/4-inch or less. And this is good for pellets too if you wanted to test pellets. So like I said, Andrew and George have that in stock. If you guys wanted to run a test or wanted them to bring it out to you, please contact them. And then they also have a couple nice videos. I guess this will be going up too, but they have a real quick one that we put together on the importance of sharp knives and knife gap setting. And it just really pops as to what happens when the knife gap isn't sharp enough or isn't tight enough, even with sharp knives, for a certain material. This is a PVC roofing material with a scrim in between. And then if you wanted more information on dedusting, you can contact them. But there's also a webinar there. It's kind of lengthy, but you're free to watch that at any time. And then that's what I had to say. I open it up for questions.